inverse relations. So you'll find that most things in mathematics have an inverse or an opposite, and usually we're talking about the basic operations, multiplication is the inverse of division, addition, subtraction, so that sort of thing. But our functions and our relations have inverses as well. So let's define it. So y equals fx, at this stage I'm calling it a relation. So it may or may not be a function. So y equals fx is a relation. Its inverse relation is simply found by swapping the x and the y's round. Okay? That would create an inverse relation. So if I've got y equals x cubed plus x, to get its inverse relation, there it is, x equals y cubed plus y. No, okay, I could go and make y the subject and what have you, but there's no need to, I don't have to. The domain of the relation becomes the range of the inverse relation because we've swapped the x and the y's around. And vice versa, so the range of the relation becomes the domain of the inverse relation. If you were to draw both curves on the same graph, you would find they would have symmetry around y equals x. So they would reflect onto each other. That means, by the way, if we have a look to the left, there's a couple of graphs there that are their own inverse relation. What would they be? The hyperbola would be one, certainly, because if you imagine y equals x there, you could fold that perfectly on. And the other one, circle, of course, because it has symmetry in every direction. They certainly are inverse relations. So y equals x squared, its domain is all real x, its range is y is greater than or equal to 0. And you may recall x equals y squared, whilst we might not have called it the inverse relation before, but we've certainly seen the graph before. X equals y squared, parabola on its side. The domain would be x is greater than or equal to 0, range would be all real y. So we can see the domain and the range basically have swapped. What we're far more interested in is inverse functions. Inverse functions. So, the inverse relation of a function, so to start off with, we have to start with a function. We find that function's inverse relation. Now that may or may not be a function, depending, because we've swapped the x and the y's around. But if it is a function, then it becomes an inverse function rather than an inverse relation. So you've got to start with a function, swap the x and the y's around, and if the answer is a function, then you have an inverse function rather than an inverse relation. So how do you test? Well, visually, I can use a horizontal line test. So remember, a vertical line test told me if it was a function. So if I'm swapping the x and the y's around, logically, if I use a horizontal line test, it will tell me if it has an inverse relation. Algebraically, we could do it this way. Swap the x and the y's around, and when you make y the subject, if it is unique, then we've got a function, an inverse function. Now what do we mean by that? So here's our parabola, y equals x squared. Horizontal line test, it fails. It's cutting into spots. So it will not have an inverse function. It'll have an inverse relation, but not an inverse function. Now, algebraically, if I swap the x and the y's around and make y the subject, I get y equals plus or minus. The mere fact that I'm saying plus or minus is telling me there's two possible things here. So it's not unique. It's not unique. So if it's not unique, then it can't be an inverse function, it must be an inverse relation. Y equals x cubed, on the other hand, yes, doesn't matter where I draw the horizontal line test, it would work. Algebraically, swap it round, x equals y cubed. So y would be the cubed root of x. Now when we're dealing with real numbers, there is only one cube root of x. So that is unique amongst the real numbers. Okay, then a beautiful thing happens. Because inverses in mathematics should cancel each other out. Like if you multiply by 2 then divide by 2, you're back to where you started from and so on. Well, the same thing should happen with these functions. So if you've got y equals function x, If you substitute the function into the inverse, so that's the notation for inverse, a -1. It doesn't mean to the power of -1. It means the inverse function or relation, depending on what we're talking about. If you were to sub the function into the inverse, you should just end up with x. The functions should, if you like, cancel each other out. And the reverse would be true as well. If you substitute the inverse into the function, you should end up with x. And to do one, let's do it here. This is a function. That would turn out to be a hyperbola. It's been shifted around the number plane a bit. It's inverse, so let's swap the x and the y's round. And I'll make y the subject. And eventually we get there. Y equals 2x plus 2 on 1 minus x. So if I substitute the function into the inverse, so looking at my answer for the inverse, everywhere I see x, I'm replacing it with the function x minus 2 on x plus 2. Now hopefully when we tidy this up, we'll just get x. Let's see what happens. Sure enough, x is what we get. But I said the reverse should be true as well. So let's have a look at that. So this time, I'm substituting 2x plus 2 on 1 minus x. Everywhere I see x in the original function, let's play around with that one. And sure enough, we get x again. So I mean, inverses and functions, they should cancel each other out. Draw the inverse relation. Well, the first thing I would do is draw in the line y equals x. And I'd probably plot some key points. Now, the point of intersection on y equals x is obviously a key point because it'll stay there. Other things like the turning points I might draw. So remember, you've got to go at 90 degrees and then go straight through the other side. Eventually, now through a lot of hard plotting, let's see what happens. Oh look, there we go, wow. Had to plot a lot of points for that one, maybe. Or I might have just told it rotate, but anyway. But if you look at that down y equals x, you can see the symmetry. So whatever that function is, that blue one, the red one, would be its inverse relation in this case, because it doesn't satisfy the horizontal line test. And then we notice the red one, the new one, doesn't satisfy the vertical line test, consequently. So that's an inverse relation, not an inverse function. So that gives us, I mentioned this the other day, but that gives us an alternative way of finding range. Okay? Because we said the domain of the inverse is the range of the original function. So rather than trying to find the range of the original function, it might be easier to find the domain of the new function. So let's pick a an easy one, y equals x squared. I'll look at that. And I'll swap the x and the y's round. I'm using capital letters though, just so I don't confuse it. So there's x equals y squared. Rearrange it. Y equals the square root of x. Yes, I know it is plus or minus, but I'm dealing with functions. So technically, I should have written x to the power of a half rather than the square root of x. But anyway, y equals the square root of x. If I had said what is the domain of that, doesn't really matter whether I had plus or minus there anyway. It's what's under the square root sign that's important. The domain of the new function is x is greater than or equal to 0. So therefore, the range of the original function must have been y is greater than or equal to 0. Let's try another one. The x squared where we moved it up 3. Same idea. If I swap the x and the y's around, the square root sign is causing the problem with the domain of this new function. So the domain of the new function would be x is greater than or equal to 3, so therefore the range of the original function must have been y is greater than or equal to 3. Did I do another one? Oh, here's an absolute value one. Y equals the absolute value of x plus 2 minus 5. So swap the x and the y's. Now this is going to be an interesting one to try and make y the subject. Here we go. X plus 5 is the absolute value of y plus 2. I want to make y the subject. So x plus 5 must be greater than or equal to 0. I'm actually not interested in the y plus 2. Remember, I'm interested in the domain. And I know absolute value always has to be positive. So I've just said, oh, well, I'm not going to try and solve it and make y the subject. I'm just going to simply say, well, I know x plus 5 is greater than or equal to 0 there. So the domain of the new function is x is greater than or equal to -5. The range, therefore, of the original function must have been. Now, obviously, those ones, they weren't hard to find the range of the original ones anyway, but I just use it to illustrate the idea that if you do get a more complicated one, you're looking at the range and I'm really not sure, maybe try this idea. It could work for you. So imagine you didn't recognise this as a semicircle. So I'd swap the x and the y's. Okay, let's make y the subject. I get x squared equals 4 minus y squared is 4 minus x squared. So y is the square root of 4 minus x squared. Yes, again, I know it's plus or minus, but we're only interested in the x values anyway, so it doesn't really matter. So we're saying 4 minus x squared is greater than or equal to 0, so x is in between minus 2 and 2. So that's the domain of the new function. Oh, but here we have to be really careful, because we know y, and notice I put little y there, has to be greater than or equal to 0, because I am talking about the positive square root. So I do have to be a little bit careful. So that now means the range of the new function is not in between minus 2 and 2, but in between 0 and 2. So it's a useful idea, but we do need to be careful, I guess is what I'm getting at. Let's look at something a bit more interesting. That one, of course, is a hyperbola. So swap the x and the y's round. Eventually I can make y the subject. Now what would cause the problem on this one? The bottom of the fraction can't equal 0. So I know the domain of the new function is all real x except x equals 1. So therefore the range of the original one was all real y except y equals 1. So there's 2h,